We're back. In this video, we're looking at another polynomial, and with this polynomial, we're going to find the real and complex zeros, going through each step, and I'm going to give you some tips as we go along, some suggestions, because this can be a rather long and time-consuming process. So I'm going to give you some tips to make this a little easier, a little less stressful. Are you ready? Okay, here we go. So let's say we have this function, negative 3x to the power of 4 plus 7x cubed plus 3x squared minus 17x minus 10. We want to find the zeros, both complex and real, for that polynomial. We begin by using the fundamental theorem of algebra. And if you recall, what this tells us is that by examining the degree of the polynomial, there exists, in this case, there exists 4 complex zeros. And with that, we then use Descartes' rule of sign. And this will help us understand what kind of zeros we have: positive, negative, or imaginary. To do this, to complete this table, we have to examine both the original function and the f of negative x, alternate. So our original function, negative 3x to the power of 4 plus 7x cubed plus 3x squared minus 17x minus 10. And we are concerned about sign changes. So we have a sign change, yes, no, yes, no. So 2 sign changes tells us that we have a possible 2 positive zeros or 0 positive zeros. So for an f of negative x, any even exponent, the sign remains the same. So having an even exponent, this remains negative 3. Odd exponent becomes negative 7x cubed, positive 3x squared, positive 17x, and our constant always remains the same. Again, looking at sign changes. No, yes, no, yes. So as far as negative zeros, we have a possible 2 or 0. And with this, our imaginary could be 0 imaginary, 2 imaginary, or 4 imaginary zeros. And before we continue, I want to say this. This step, using Descartes' rule of sign, this step is optional. It is optional for us. We don't technically need to do this step. But what it does tell us is what kind of zeros exist in the polynomial. And how that's useful is, let's say I go through my next phase and I find that we have a positive 0. Well, by this, if I find one positive 0, I know there must be another positive 0. Or if I find a negative 0, that tells me that there must be another negative 0. So that's kind of, this is how the table is useful to us. It helps us to determine which root to test next. So it is optional, but it is useful. Okay? So once we've determined what types we have, we're going to use the rational root test. To examine the possible locations. So this is our P and Q. So P, factors of negative 10, that would be positive negative 1, positive negative 2, positive negative 5, and positive negative 10. And then factors of Q are constant, or coefficient I should say, positive negative 1 and positive negative 3. So that will give us the possibilities: 1 and 1, so positive negative 1, 1 and 3, 1/3, 2 and 1, 2 and 3, 5 and 1, 5 and 3, 10 and 1, 10 and 3. So these are the possibilities. There are here 16 possible roots or zeros, whatever term you want to use there. You can use them interchangeably. So 16 possibilities. We had looked and said that positive 1, we always want to test positive 1 first. So is it a 0? Is positive 1 a 0? So you might ask, couldn't we put 1 into our function and hope to get 0 out of it and that tell us whether it's a 0 or not? You could do that, but the issue with that process is if it is a 0, we want to know what new equation we get after dividing by it. And using synthetic division, we get that while we go through the process. And that's kind of the reason why we use synthetic division every time and not placing the number into the function. Okay? So let's try placing 1 in. So we place 1 in, -3, 7, 3, -17, -10. Okay, so going through this really quickly, drop to -3, -3, +4, +4, 7, +7, -10, and -10. And you'll notice we do not get 0. The remainder is not 0. But I should add, if you notice quickly, if this was only a +10, it would have worked for us. So it's not a 0, but we are close. What I mean by that is positive 1 got us really close to a number that led us to a remainder of 0. So if positive 1 put us that close, what if we had -1? So x of -1. So let's go through this whole thing again. So -3, 7, 3, -17, -10. Okay, going through this. -3, -1, -3 is +3, 10, -10, +7. Hold on, something's not right here. -7, there we go. -7, +7, -10, -1, -10 gives us +10, which gives us a remainder of 0. Yes, this is exactly what we wanted. So, recapping, positive 1 led us to a number at the very end that was very close to giving us 0. So I tried the negative alternate to that. So when I used -1, it led me, in fact, to a remainder of 0 that time. So that might not always work, but it is something to try when you're going through a process. So with -1 being a 0, what we get, our function now is x plus 1, and then we are left with -3x to the power of 3 because we started with a cube power of 4, plus 10x squared minus 7x minus 10. So with that, I had said earlier Descartes' rule of signs is really useful. How it is useful here, we just found that -1 is a 0. And by Descartes' rule of sign, if I have a negative number, there must be another negative number as well. See, I would not have known that without doing this. So having -1 as a 0, we're going to try another negative number. And this is where we just test. Just pick a number and test. So let's say we have, let's try -2. So let's try -2. So we're using our new polynomial, -3, +10, -7, -10. Okay. Drop to -3, +6, 16, -32, -39, -2, -39. That would be +78, which I don't need to solve that. I know it's not 0. So what we can say is x plus 2 is not a factor of the function. Okay, so -2 didn't work. Let's just try another one. Let's try -2/3 from our list. Okay, so -3, 10, -7, -10. Okay, so I'm thinking drop to -3. -2/3 of -3, that's +6/3, or just 2. 10 and 2 give us 12. -2/3 of 12 is -24/3, or just -8. So you have -15. -2/3 of -15 is +30/3, which is just 10, which gives us 0. Yeah, so that's good. We wanted that. So we have our second -0. So our function now looks like x plus 1, x plus 2/3. So there are the two negative zeros. We're left with -3x squared plus 12x minus 15. And I said previously that once you get to a quadratic, solve it by other means. Don't continue this synthetic division process, although it could work for you. We have other tools available that could be a little faster. So we look at this, and my first option typically would be to factor. So -3, +12, -15. Again, we're trying to factor this. Let's see, -3, +1, -5, 3. It doesn't work for us. And if you keep trying this yourself, you'll notice that this is not factorable. This is not factorable. And that's interesting, because if it was factorable, what we would have actually have found from that is two additional real roots. So we would have had probably 2 negative roots, and then from this we would have had 2 positive roots, totaling to our 4. So this does not factor. So let's see what happens from this. And I'm going to use this time, since factoring didn't work, I'm going to use the great quadratic formula. So I'm going to go through this rather quickly, because again, you could pause it easily and just do it yourself. So we get -12 plus or minus -36 over -6. So I see a negative in our radical, which leads us to pulling an I out from that, which -12 divided by -6 is +2. When I divide this term by -6, the positive negative would just go positive negative still. So I'm going to disregard the negative here when I divide the square root of 36. So we know square root of 36 is 6. So 6 divided by 6 is 1, which just leaves us with I. And we find that we got an imaginary 0. Or I should say zeros. And this has been said before, imaginary zeros come in pairs. And being more descriptive, they come in conjugates. So a term that we have heard of before, probably the first month of the year, conjugate. That's where we have 2 plus I, and then we would have its conjugate 2 minus I. So they come in pairs and always in conjugates. That's important to know. So we have now 2 negative roots, 2 imaginary roots, which totals to our 4 complex, as we saw at the beginning. Now, we are at the very end. So let's finish this up by writing the factors. X plus 1, x plus 2/3, and then for our imaginary roots, I would write x minus 2 plus I, and then x minus 2 minus I. Yes, it's always subtraction and then the imaginary root. It's just, if I put addition there, it changes the root a little bit. So we always, yes, do subtract the imaginary root when you find it, if it exists. So going through this whole process again, it can be rather lengthy. If we choose the wrong zeros to test, it could add time to this problem. That's why we want to use those initial tests, the fundamental theorem of algebra, Descartes' rule of sign, other things, to get to a quadratic. And with a quadratic, we try to factor, or if that fails us, we can use the quadratic formula. And typically, from this quadratic equation, this is where we will find our imaginary zeros. That's typically where we find our imaginary zeros. So the zeros of this polynomial are x equals -1, -2/3, 2 plus I, and 2 minus I. So before we end this video, before we end this little quick example, I want to say, if you have any questions, pause it, replay it, post any questions you have, comments you have in the classroom, and I'll do my best to answer them as we go along. But before you go, I would like for you to take time to factor and solve this next polynomial. So let's say we have f of x equals 2x to the power of 4 minus 7x cubed minus 2x squared minus 7x minus 4. So again, before you come into class, I would like for you to find all the zeros. Okay, that's real and complex, or real and imaginary. Find all complex zeros and write f of x in factored form. So take time to do that, and see you later.